Okay, so let's talk about accurate response. The key part of accurate response, the key resource which enables us to do accurate response type of strategies is reactive capacity. As the name suggests, this is a capacity that allows us to react to demand, which means it has a small or a short lead time. So look at the picture on the slide. The black horizontal line is time. So on the left is the time is proceeding towards the right from left to right. So the first event that happens is you place a normal order with your regular capacity. Now, sometimes your regular capacity and the reactive capacity will be two different suppliers. Regular capacity could be a long lead time supplier, which is very low cost. And reactive capacity could be a more expensive short lead time supplier. For example, in automotive, you may have a supplier in Asia, which is a long lead time and cheaper supplier. And for the same parts you could get built in Canada, which might be a short lead time but more expensive supplier. Okay. In other instances, it may be the same company, but they may have two different offerings. For lower cost, they take longer, but they build the part. But if you want the part delivered early, expedited with a short lead time, then you pay them more and they will expedite the order and build the part quickly for you. So in that case, reactive capacity and efficient capacity may be part of the same company or the same supplier. It's just you pick the contract, you pick the cheaper contract or the expensive contract whenever you place the order. Okay. So in any case, when we are out here in time now, the blue bar right here, okay, the blue horizontal the red bracket right here represents the selling season. Okay, so you can see well before the red bracket starts out here, we can place an order, and we have to place an order early enough that we have enough time for our lead time to happen and our goods to arrive before the selling season starts. So you'll notice that this blue bracket, which is labeled efficient capacity production, this is the time your regular efficient, by efficient I mean cost efficient, it's cheaper. There's your cost efficient capacity takes. So this includes transportation time, production time, all of that. Actually, transportation time is represented by the truck. So this includes the, you send the order over, they acquire raw materials, they produce the goods, and then they send the goods to you, which is the transportation time. So the production and transportation time together needs to happen and end before the selling season starts, so that you have goods in your retail stores, in your warehouses before the start of the selling season. So the normal order placed is placed very early. How early depends on the lead time of your efficient capacity. If your efficient capacity is in Asia, you might need a 3 or 4 month, there might be a 3 or 4 month lead time, and you might want to order 4 months before the selling season starts. If your efficient capacity is closer or just faster, so it depends on the lead time, how early you have to place the normal order. Okay, now once the normal order is shown in blue, and then the second reactive order or the late order is shown in green. So when the selling season starts, notice you only have the blue bar to sell. So blue bar represents product you're selling, which was built using efficient capacity. Once you have a little bit of demand data from the selling season, so notice where the late order placed arrow is, you're just a little bit into the selling season, maybe a few weeks, maybe a month. So at that point, you have gathered some data from the selling season, and you kind of know which SKUs are selling better, which SKUs are not selling as expected, and you can use this data to revise and update your forecasts. When you revise and update your forecast, you may realize, okay, I need to order more of X and I don't need more of Y, and so on and so forth. Also, because when you place the normal order, you already knew you have some reactive capacity. So even if you expected to sell, let's say 100 of an item, but you were not sure you'll be able to sell 100. Maybe you ordered only 80. And now that the season starts and those 80 are depleting very fast, you say, oh, I need to place not just 20 more, I need to place an order for 40 more of this item to get to 120 total, because, I thought I was going to sell 100, but it seems like I might sell 120 now. The season is going really well. Things like that. Some SKUs, you may have only ordered a starter or testing quantity. So let me just order 50 units or something to test this in the market. And in the early season, if those 50 sell very quickly, you say, okay, now let me place a big order. Okay, maybe I can, sell another 100 or something. Obviously, reactive capacity does not have zero lead time. So when the late order is placed right here, the green bracket here shows you the shorter lead time reactive capacity. Notice this green bracket is much smaller than this blue bracket. So reactive capacity has a much shorter lead time than your regular capacity. And then the truck represents the transportation time. Once the reactive capacity has produced the goods and the truck has transported them, now you can start selling items produced with the reactive capacity, and you're also selling items produced with the regular capacity, which is the blue line. Okay, so that's what reactive capacity is. It allows you to react to early demand signals. Sometimes, the late order is placed just before the season starts, because sometimes just before the season starts, you have more clarity about what you're going to order, and maybe your reactive capacity lead time is still so long that you don't want to wait into the season. So sometimes you might see it being done that you have a first order placed well in advance of the season, and then very close to the start of the season, just before the start of the season, you place a second order. You haven't observed any real demand yet, but that close to the season, you have some signals. Like maybe you did some market study, you tested your products with customers. Maybe you can see the competitors' offering now, and you can compare your offering with the competitor's catalog or their offering and get a better sense of what's going to sell better, right? But that is not the traditional way we think of reactive capacity. But it's the same idea that the closer you get to the season, the more accurate your forecasts become. When you have more accurate forecasts, you place your second order. Okay. Obviously, once you have actual demand data from the first few weeks or month of the season, that is really useful in reducing the error of your forecast, and you can really get accurate forecasts once you have initial data. Right? So the best use of reactive capacity is like what I have shown on this diagram, but you may see some companies where the reactive capacity is also very long lead time, shorter than regular capacity, but not as short as I've shown here. They may have to place the second order right at the beginning of the selling season, where the market dynamics are clear. You know what products your competitors are putting out, what their pricing is, and based on these up-to-date market dynamics or some very early, some people order, let's say, the fall season starts, and people need some sort of outerwear. Some people are early birds. They'll order a little bit early. So maybe you have some early sales of very limited SKUs, and you use those to predict sales of other SKUs. So this stuff you could do in the very close to the season that can give you more accurate forecast. But if you wait to get some actual demand data, that'll really improve the accuracy of your forecasts. Right? So this is how we use reactive capacity, and this setup of placing an initial order and then placing a second order when you have much more accurate forecasts based on initial season data, initial sales data from the beginning of the season. This whole system is, in summary, what we call accurate response. Okay. Now, this is an example from a real company, Sport Obermeyer's. And this shows you the improvement in forecast accuracy. So on the left, you have the initial forecast of women's parkas, which are jackets, well before winter. So you're forecasting this maybe in spring or early summer because it's going to take you, several months to get them produced in Asia and then shipped over. So you can notice that the initial forecast is on the x-axis and the actual sales that happened, and you observe the actual sales at the end of the year. So this is historical data. This is last year's data. You can see that the actual sales and the forecast do not lie on a straight 45-degree line. Sometimes your forecast is like 600 and your actual sales is only like 100. See the point right here? You thought you were going to sell 600 of this parka and you only sold like 100. Okay, sometimes you predicted 500 here and you ended up selling 700. And you might ask, how did that happen? If we predicted 500, how did we end up selling 700? Well, maybe they produced 200 extra on an emergency order, or maybe when they were placing the order, they thought, oh, this parka might potentially take off. It has a lot of, maybe it has a high profit margin. We can take a risk. So remember I showed you sometimes you can order above the forecasted quantity because the product is so profitable that any additional units you sell give you a lot of money. So let me just show you. If you go back right here, so your forecast quantity, let's say is 100. Sometimes you're going to order more than 100 because the benefit of additional units, if they sell, is a lot, and the cost of having additional units is not very high. So if the benefit versus cost trade-off is like that, you can order above forecasted quantity. So you can see that happening here. They predicted they were going to sell 500. They end up selling like 700. So they had ordered extra, or they got it made on an emergency or rushed order where it would have costed them a lot more, but they're still able to get the higher quantity. But anyway, this dispersion in the points shows you there's a lot of variability, right? You predict 500, you end up with 100 or 700. Look at the forecast error. It's almost like 100%. Plus minus 5. Well, if you're at 500, you're going plus minus 400 on each side. Right, so almost 100%, 80% MAPE or something like that on these items here. So there's a lot of variability in the initial forecast. It's very hard to predict the sales sitting months before the selling season. Now notice the middle graph. The middle graph is when you have incorporated 20% of the sales data, which means that if your selling season is 4 months long, 20% of the selling season has passed. For a 4-month season, 20% would be like a few weeks, like 3 weeks or something, right? So you wait a few weeks and you get the data on the products for the sales in the first 3 weeks, and you use this as an input to your statistical forecasting software. You say this is the initial sales. It uses that as an input to revise the forecast. And notice how the dispersion has reduced. Okay, especially for parkas which are going to sell between 0 and 1,000 units, which is most of their parkas. The dispersion is very low. Okay, the MAPE has reduced. The absolute deviation from the average forecast has gone down. So you can see it's a much tighter scatter plot. Okay, so this is the improvement in forecasting accuracy that Accurate Response wants to exploit by using reactive capacity. So now that we have a much better idea exactly how much we're going to sell, we can put in a second order. And because we did not produce everything we needed in the first order, we left some for reactive capacity to plug the gap. You're going to use short lead time reactive capacity, and now we're going to be very accurate. So with the second order, the total quantity produced is going to be very accurate because we have very accurate forecasts now. And notice once you've observed 80% of the sales, your forecast is essentially the actual sales is almost like extremely accurate, right? Whatever you forecast, exactly how much you sell. But this may be too late to place like a third order depending on your lead time, right? So this is like the graph on the right is just to show you the more actual data you observe, the more accurate your forecast becomes. But this is probably too late to do anything about it right now when you have observed 80% of the sales. 80% season is passed, right? So the middle graph is where the second order is going to go, and the first graph is well before the season where the first order is going to go. So you can see that the forecast accuracy improves, which is why this late order placed, the second order placed, you're going to hit the nail on the head. You're not going to have extra units left unsold, or too little units, which you are losing sales now, you're going to really match the demand and the supply with the second order. So that's the accurate response. That's the accuracy coming in. The accuracy in the forecast coming from observing initial sales in the selling season, and that being able to benefit from this accuracy because of the low lead time reactive capacity. Okay, so now not every item you're going to put in the second order, the reactive capacity order, because let's say you have a white t-shirt that you've been selling for the past 50 years, and it's a very predictable item, and based on historical sales, they can very accurately predict exactly how much white t-shirts you're going to sell in summer. Okay, let's say it's a summer seasonal clothing item. And so you might say, well, I have a very accurate forecast. Why don't I just use the entire efficient capacity to produce this t-shirt, because I don't have a lot of errors of mismatching supply and demand. I'm going to hit the nail on the head. I have a very accurate forecast. I'm going to have very few extra units, if any, or I'm going to have if I have a shortage, it'll be a very little shortage. I will be, if this demand turns out to be 1,000, I may have produced 950, but I'm not going to be very far off from the actual demand. So the loss either way, whether producing too little or too high, either way, the loss is not going to be big because I'm going to be very close to the actual demand. So what's the point of producing only half the quantity of white t-shirts or 70% quantity of white t-shirts and leaving 30% for reactive capacity, because my unit cost will go up. Reactive capacity is usually more expensive. Why not I just produce the entire quantity I expect to sell using efficient capacity, because my forecast is accurate and my unit cost will be lower. I'll make more money on every shirt, right? So for predictable demand items, you're going to be producing most of the quantity that you expect to sell, or all of the quantity on efficient capacity. Which is why, if you think back to the beginning of this lecture, I said knowing the forecast error is really important. Even if you think forecasting is not going to be accurate for your situation, you have to do the forecasting activities to get a sense of the forecast error, because not all SKUs, not all categories, not all items will have the exact same amount of forecast error. Some will have more forecast error. Some will have less forecast error. Less forecast errors are your predictable items. They are awesome. They're good for you because you can get them produced on cheap capacity with long lead times. Okay, so that's what you do with those. For your unpredictable demand items, where your forecast has a big error, you can be off by a lot, right? You can think you're going to sell 500, but you only sell 100. Now you have 400 parkas left in your shop that you don't know what to do with, and winter is ending. Or you thought you were going to sell 500, you ended up selling 800. The demand is for 800. If you don't get that 300 extra, you're going to lose 300 customer orders, and that's a lot of revenue and money lost. So either you're going to have lost sales, or you're going to have an excess inventory at the end of the season. You're going to have error one way or the other because you just can't predict it. It's very hard to predict. For those items, it's very useful to use reactive capacity. You have an initial forecast, but you're not going to produce, let's say your initial forecast is 500. You're not going to produce 500 on the efficient capacity. Initial forecast is 500. Let's say you're going to say, okay, maybe I'm going to produce 40% on the efficient capacity. So you only give an order for 200 to the efficient capacity. Then as the season starts, because you want to have some in stock to start off the season, you can't, have zero in stock. Then you'll never learn the true demand of the item because you have nothing in stock. So let's say you produce 200 units out of the 500 on efficient capacity. You start the season with this inventory of 200 in this shop. You look at the rate of sales. Are you selling 1 per day? Are you selling 10 per day? Are you selling 20 parkas per day? After 2 weeks, you look at your rate of sales. If your rate of sales is so high that you're going to go, you're going to end up selling 800 in the whole season, you place an order for the remaining 600. You already got 200. If you want to sell 800, you have to place 600 more, right? So depending on the rate of sales early in the season, you place the order with reactive capacity. And the reactive capacity order, you can see the size of the arrows is substantial compared to the efficient capacity order. Maybe you produce 200 on efficient capacity, you might end up producing 300, 400, 500 on the reactive capacity. They're going to be, both orders are going to be equal, not equal, but roughly equal in terms of magnitude. You're going to use a lot of reactive capacity on these items because you can't predict them. Whereas some of your efficient items, you may discover that a few of them, the sales are doing very well. better than you expected. So you can also produce a few of those SKUs in reactive capacity, right, to not have lost sales. Okay, but the size of the error shows you that most of the quantity and most of the predictable SKUs go to efficient capacity, whereas for unpredictable SKUs, a big chunk will go to efficient capacity and a big chunk will go to reactive capacity. Okay, let's see if I can show you something here. Okay, I can draw. So let's say this is your forecast. This is your forecast. On the x-axis we have forecast, y-axis we have actual. Okay, or yeah, or we can just look at the forecast error. So let's erase this. Let's do a little bit better job. Okay, let's say we have an SKU like this red dress, okay, and we expect to sell a certain quantity. Okay, let's say this is 1,000 units. That's our forecast. But we have a big forecast error on these type of SKUs. We know that these type of dresses are very unpredictable from past experience. Last year, we made a forecast for a dress like this, and the error was huge. And the year before, for our initial forecast, right? Our initial forecast is always off by a lot. For these dresses, could be actual sales could be a lot low, could be a lot high. So we have a big forecast error. Okay, so it might end up that we only sell 200, or it might end up that we end up selling 1,600. So it could be big variations around 1,000. But even though our forecast error is large, we know that there's a very high chance, almost surely we're going to sell at least 200. There is a minimum. And maybe we can take a little bit of risk and go a little bit above the minimum and say, okay, there's an 80% chance I'm going to sell at least 300 or 400. So you go between the forecasted value, okay, FC, the forecast, and the minimum. The minimum you get by looking at how big the forecast errors for these type of products were in the past. So you have an idea, okay, in the past, dresses forecast error is about plus minus 500 or plus minus 600, whatever, right? So you have an idea of the error from past data, past forecast and past actual sales. So you say, okay, if my forecast says 1,000, based on past data, I know I'll be able to sell 300. I have a very strong chance of being able to sell at least 300. So the 300 will go to efficient capacity. And then you'll observe initial sales. And if the initial sales say, oh, you're only going to end up selling 400 total, then you only put 100 here. But if your initial sales say, oh, you're on track to sell 1,200 total, you only have 300, so you're going to place an order of 900 here, right? And so for these unpredictable items, both this order and this order can be large. But for predictable items, this order will be very large and this order will tend to be small because your error is small. So even if your demand exceeds your forecast, it's not going to exceed it by too much. Okay? So that's how you match the type of demand you have with the type of capacity you have. It's almost like a fit. Remember we saw a fit for supply chain strategy, like innovative items need reactive supply chains and functional products need efficient supply chains. It's kind of like the same idea, but applied at the SKU level, where within one company, you have many SKUs. Some are predictable, some are unpredictable. They don't have to be innovative. They could just be like a dress, but it's unpredictable because of colors. You don't know which color is going to hit off based on some TikTok video, in around Christmas or around Thanksgiving or something like that, right? And so at the SKU level, there's a lot of variability, even though it's not an innovative item. But again, it's the same idea overall. You're trying to match the type of demand with a type of capacity. Okay? So let's look at the accurate response step by step. The first step is you create an initial forecast. That's well before the selling season, so you have time to use your efficient capacity with long lead times. You estimate forecast error. Okay, we're going to talk about this in more detail. this could be, how we estimate that. One way you can estimate forecast error is to look at your team. Let's say you have a team of 5 or 10 or 7 people doing the forecasting for certain SKUs. And you can look at if the same team or similar teams worked last year. You can say when these teams disagree with each other about the forecast for an SKU, the differences in their forecasts, they can predict the actual forecast error that happens by the end of the season. So last year, for SKUs where these teams differed by plus minus 1,000 units, the forecast error was plus minus 2,000 units. When these teams differed by plus minus 100 only, the forecast error was plus minus 150 only. So you will have this mapping of how the agreement of the team members can predict the forecast error based on historical data, historical performance of these teams. So based on that relationship, when you have the teams agreeing or disagreeing on their forecast this year, you can use that agreement or disagreement to predict what will be the forecast error for the SKUs this year. Once you have the forecast error tells you which SKUs are predictable and which ones are unpredictable, because unpredictable by definition has a high forecast error. Predictable by definition has a lower forecast error. Okay, so this is important to estimate the forecast error because that tells you, where the product goes, predictable, unpredictable, and what type of capacity you're gonna use. Okay. Then we go to assign. So assign means you determine what quantity to assign to the efficient long lead time capacity. So for predictable items, you may assign most or all of the quantity to efficient capacity. For unpredictable items, you may only assign 30%, 40%, 50%, some thing like that, depending on, how sure you are about what you'll be able to sell of those, depending on the forecast error, obviously, right? And now it's not just two buckets. It's not just you have predictable items where your forecast is like 99% accurate and unpredictable items where your forecast is not at all accurate. You have a range. And so the ones which are very predictable, you might produce the entire quantity with efficient capacity. The ones which are highly unpredictable, you might produce 90% of the capacity, quantity or 80% in reactive capacity. And the one in the middle, you may do half efficient capacity, half reactive capacity. So it's a whole continuum of SKUs that you have. So based on where they are in the continuum, unpredictable, predictable scale, you assign the quantities to efficient capacity. Remember, you need to have some quantity of an SKU to do some initial sales in the season. That will give you the signal for the second order. So once your initial sales data becomes available, because you produce some quantity of the SKUs, you don't have zero quantity, you are able to make some sales. Then you look at the rate of sale. How much are you selling per day, per week? Like how fast is this SKU moving? And then you use this to update your forecast. As shown before, the forecast become a lot more accurate once you've observed 10, 15, 20% of the season has passed. So maybe a few weeks have passed or a month has passed. Now your forecasts are a lot more accurate. Now you revise the forecast based on the new accurate forecast, like they replaced your old forecast. And now based on this forecast, you determine the reactive capacity production quantities. Okay, and that's your second order you place after the season has started, and that's how you do accurate response. Okay. Now, reactive capacity is expensive, so you don't need a lot of reactive capacity. Some people have done an analysis and they've shown that if you, of the total capacity you need to produce enough quantity for your winter clothes or summer clothes or whatever thing you're looking at, if about 25% of that is reactive capacity or even 20%, that gets you most of the benefit of reactive capacity. So you don't need to have like half, 50% efficient, 50% reactive. You could have 60 or 70% efficient capacity and only 25, 30% or 20% reactive capacity. Okay, because a lot of your SKUs may have predictable or relatively predictable sales and you can produce all of them in efficient capacity. You don't need too much reactive capacity. Again, exactly how much you need or how much is the best for you depends on how many SKUs you have, how unpredictable the sales are, what are the forecast errors usually for those SKUs, and then you can estimate based on historical data how much quantity do you need to be produced in the season as reactive capacity. Then you can, tell your supplier, okay, I need, or find short lead time suppliers, or tell your supplier to have a short lead time production run, which may be more expensive. You can pay them more, but you can plan your supply base according to that. Okay. Now, what SKUs and what quantities do we order early? I've touched upon this already. You order low risk SKUs. Low risk means there's a low risk that you'll not be able to sell it, which means there's a high chance you're going to be able to sell it. So when the forecast error is low, you have low risk. You know pretty well how much you're going to be able to sell, right? So that's what we do. We leave risky and unpredictable part of demand to be supplied by the reactive capacity. Let's go through an example. So this is from the Fisher and Raman did excellent work. I believe I have the reference to their paper in the notes of this slide or the next slide. So if you want to get the exact research paper, it's quite mathematical. I'm presenting to you the main ideas in much simpler way, and their paper will have a lot more mathematical equations, but I've kind of extracted the key insights out, and I'm going to present those to you. So you can download the exact paper if you want to. The reference to the paper is given in the notes for this slide or the next slide. So they worked with Sport Obermeyer, Fisher and Raman. Fisher was, I believe, at Wharton School, Wharton Business School in University of Pennsylvania, and I believe Raman was at Harvard Business School. Anyway, in the 1990s, they worked with Sport Obermeyer to solve this problem Sport Obermeyer had about how do you implement accurate response, right? And they came up with certain mathematical calculations which can help you really fine-tune and optimize your accurate response orders, like what to order initially, what to order late. We're going to do a little bit simple version of their calculations, which is gets you most of the way there. And I'm going to show you how this will look like in practice. So this is the information you have. Let's say you're going to do this for a product category. Remember, at the category level, we have historical data. You can do a statistical forecast. Okay. And so this is a category of women's parkas, and we have 10 items in this category, and we have given them names. Like, marketing team, they love to have these code names for products, or maybe these are just the names of these parkas, right? So we have Party, Ranger, Electra, Anita, Daphne, Entice, Gale, Isle, Perry, and Spain. These are our 10 parkas for women's parkas. And the women's parkas category has existed for decades, and we have a lot of historical data for the whole category at the category level. But these 10 parkas are all new. We have modified the design or done something or changed the colors. So we don't have an exact copy of these parkas last year to use historical data at the item level for the parka level. But for the category, we have data how women's parkas sell. Based on category level data, we do a statistical forecast, and we realize that, okay, we are going to sell 15,000 parkas this season. Or the parkas are very profitable. The forecast might say we are going to sell 14,000 and we want to order 1,000 extra, because extra parkas, with a small discount, you can get rid of them, still sell them. But if you lose a sale, you lose a lot of money. So maybe you're ordering a little bit higher than forecast, or the forecast is 15,000, you're ordering 15,000. Either way, based on the category level forecast, you have decided you want 15,000 women's parkas. But you don't know how many of the 15,000 will be Party, how many of the 15,000 will be Ranger, how many of the 15,000 will be Electra, and so on and so forth. Now you have to break up the 15,000 across these 10 SKUs. Okay. We also know that last year, the forecast errors had a standard deviation of 400. So if you took out all the women's parkas last year, you looked at the initial forecast you had for them, not the updated accurate forecast in the season, the initial forecast, and you look at the actual quantity sold, and you look at the forecast error from last year's data, you see that for this category, on average, the forecast error is plus minus 400. Okay, you're off by about 400. Or you just list those forecast errors in a column in Excel. You calculate the standard deviation. The standard deviation is 400 units. The average error should be 0, because on average will be high or low, and the plus minus will cancel out. So on average, the average error is 0, but sometimes you have an error which is plus, sometimes your error is negative. The standard deviation around 0 is 400, or the average error is plus minus 400. So we know that from last year. So it's all category level data. Nothing in this is item level, SKU level. Okay. In this category, our error, forecasting error, tends to be plus minus 400. We need to order 15,000 based on statistical forecast for this category. We also know that whatever suppliers we have who make parkas for us, we have 67% efficient capacity in our supply base and 33% reactive capacity. So we have, some suppliers that give us most of our capacity and they give us about 67% of our capacity. And this mix might be for your entire winter product base, not just for parkas, and you don't want to use all the reactive capacity by parkas and leave the other categories hanging dry. So you know that for any category you can produce 33% in reactive capacity, up to 33%, and the rest you have to produce in efficient capacity. Okay, so if you split 15,000 by 2/3 and 1/3, 33% of 15,000 is 5,000. So you can leave 5,000 for reactive capacity, and 10,000, which is 67% times 15,000. This 10,000 is what you have to produce with efficient capacity. So we have to place an early order of 10,000 units. If you go back to this slide, this early order right here, this normal order, this is going to be 10,000 for us for this parkas, and the late order is going to be up to 5,000. Okay, it may be less, but we have about up to 5,000 reactive capacity to use in the late order. Okay, so let's look at this data. This is the data from our forecasting team. We have 5 people. They may be sales executives, store managers. We have put them together. They're our forecasting team. And for each new SKU each new parka we are launching, each person gives a forecast. So the forecast member 1 says that the party parka is going to sell 3,300 units. The Ranger parka is going to sell 2,700 units. They don't all agree. Look at Anita. The first person thinks it's going to sell 1,850. The second person thinks it's going to sell 2,450. The fourth person thinks it's going to not sell very well, 1,100, right? And so on. So they don't always agree, right? But we have forced them to make sure their total add up to 15,000. Why? If we did not force them to do that, they may get super excited by all 10 parkas. Maybe they like the designs of all 10 of them, and they may forecast each parka to be selling 3,000 to 4,000, and they may give you a forecast of 40,000 parkas to sell. But from historical data, you've never sold 40,000 women's parkas. So what's going to change this year that's going to make it such a drastic change? From historical data that you're expected to sell 15,000 women's parkas this year. So you tell them to scale their forecast to make sure the total is 15,000. So all judges have scaled their forecast to make sure they're not forecasting beyond 15,000, because the category level forecast is more accurate than the item level forecast. So the total has to match the category level forecast, because these are all the SKUs in our category. Okay, so this is the data we have from our forecasting group. They've looked at the product, they've used their experience with parkas, and these are the numbers they've given us. So we can calculate the average forecast for each parka by averaging across the rows. So for the party, you add up these numbers, 3,300 plus 3,700 plus 2,650 plus 2,800 plus 4,000. Sum them all up, divide by 5 because you have 5 forecasts, and you get the average forecast for each parka. And based on the average forecast, you can know, okay, that's your forecast, item level forecast, right? The average would be a good way to combine these forecasts. But you can do one better. You can look at the differences between the people and use this to estimate the forecast error. Okay, how do we do that? So Fisher and Raman in their paper proposed this formula right here. So what you take is, it looks kind of complicated, but it's not that bad. I'm going to explain what you do. So Fij is forecast for SKU I by the forecaster J. So F11 is 3,300 because item 1 is party and forecaster 1 is F1. So F11 is 3,300. Okay. So what you're going to do is you're going to go across a row. Okay. So you take this number. You're going to subtract the average of the first row, the average forecast for party. Average forecast for party is mu I. Mu is the average for item 1 when I is 1. So mu 1 is the average forecast for item 1, party. Okay. And F11, F12, F13, F14, F15 are these 5 forecasts in the top row right here. You take each forecast, you subtract the average, and you square the difference. Some of the differences will be positive, some will be negative. For example, 2650 is the minimum forecast. The average of these 5 numbers is definitely going to be above 2650. So when you do 2650 minus the average, you get a negative number. But you're going to square that number, so it's going to become a positive number. So you get 5 positive numbers. You add them up. You divide by n minus 1, where n is the number of points, 5 points, 5 forecasters. So you divide by 4. 5 minus 1 is 4. So you divide by n minus 1, you take a square root, and that gives you SI, which is the standard deviation for this forecast. So this is what I've done. I've taken the average of each row and put that here. So the average for the first row for party is 3290. So I calculated that in Excel. I put that here. Then I use this formula to calculate the standard deviation. I put it here. Okay. Now, actually this should be here. Okay, so once I find the standard deviation for each item using this formula, I calculate the average across this column. Okay. And what do I find? What I find is that on average, the standard deviations are 323. However, if you go back to the problem, we know that historically, the forecast errors, the standard deviation is up to 400. So I'm underestimating the forecast error here. I'm thinking my forecasts are more accurate than they historically have been. So I can rescale this column. What I'm going to do is I'm going to get a scaled standard deviation. I take the 400 historic value, which I trust, so I know my forecast error has to be on the scale of plus minus 400. I divide the 400 by this average I obtained from this column, 323, and I multiply each of these values by this ratio. So I multiply 575 multiplied by 400 divided by 323, I get 796. And so on. So I rescale the standard deviations, and now after rescaling, when I take an average of this column, I get 400, which matches the historical standard deviation. Okay. Now that I have the average, forecast, and the standard deviations correctly scaled, I can now figure out how much to order so that my total is 10,000. Where did I get 10,000? From the breakup. I know that I have to order at least 67% of the total quantity in my efficient capacity, because my reactive capacity can only do 1/3, can only do up to 5,000 for this category. So I don't want to use up more than this category's share of the reactive capacity. So if I leave all of the 5,000 that I can for reactive capacity, I must place orders right now for 10,000 units. So I know that my order quantity has to add up to 10,000. So what I do is I decide this initial order quantity by taking the mean of each item plus a value k times the scaled standard deviation. So I'm going to take 3290 plus k times 796, so that's going to give me 2400. But what is k? I pick a value for k. I play around with k. I start with, let's say, 1. I go up or down until the value of k gives me these numbers which sum to 10,000. So I'm just searching for k. I don't know what k is, but I pick a value of k which gives me 10,000 units total, and then I'm going to use that value of k, and these are going to be my order quantities. So let me show you how to do all this in Excel quickly. Okay, so this is our original data. This is the data that your forecasting team gives you. So let me copy paste this data, and we're going to go to Excel. Okay, let's zoom in so you can see it well, and we just pasted our data in Excel. Okay, so we can calculate the average forecast, average of F. That's just the average function across the rows. Okay, and you'll notice, and I can total that, the sum will also match to 15,000. Okay, And you'll notice that these numbers here are exactly what I get on this slide. Average forecast 3290, 2420, 3290, 2420. Okay, so that's the average. Now I'm going to find the standard deviation using this formula. To do that, standard deviation, SI, okay, I am going to add up a lot of terms. The first term I add up is this minus the average squared plus the second term, this minus the average squared plus this. This is a very standard deviation formula. If you have a bunch of data points, you find the standard deviation by taking each data point and subtracting the mean, squaring it, dividing by n minus 1, taking the square root. It's a very standard deviation formula. You may have forgotten it, but if you go back to Stats 101 and you look up the standard deviation formula, if you have a bunch of data points, how do you find the standard deviation? You're going to be using this formula. Okay, you can do this minus the average squared plus this minus the average squared, and now the last one plus the last data point minus the average squared. Okay, so this whole thing is going to be divided by n minus 1, which is 5 minus 1, which is 4. And then we have to take a square root of the whole thing. So I can just do it here by putting in standard deviation, or sorry, square root, and put in brackets of the whole thing. Okay, so I got 575. And if you look, I got 575 standard deviation. Okay. Let me show you how, if you use the standard deviation function in Excel, stdev.s on these 5 values, you get the exact same answer. Instead of typing this whole long formula, which is given here, the shortcut is, I want to show you that the formula works. The shortcut is S, don't use .p, because that divides by n, not n minus 1. Do it S. stdev.s in Excel, and then select these 5 values. Do not select the average. Remember, do not select the average, just the raw 5 forecasts. And if you have 7 forecasters, you'll get 7 values. Select all 7. You get 10 forecasters. You have 10 columns. Select all 10. So 5 is nothing magical about 5. I'm just assuming I had 5 people doing the forecasting. If you have 4 people, you'll select 4. You have 10 people, you select 10 values. Each person gets their own column, right? So the number of persons could vary, but that's how many columns you have for the forecast, right? So you get a standard deviation. I'm just round it to the nearest integer, and I can drag it down. Okay. Now, if you calculate the average of this column, okay, that comes to 323, which is I'm showing you right here. But historically, this average has been 400. So I know that this doesn't look realistic. Historically, my forecast standard deviation has been 400. Maybe I'm underestimating the error. So I'm going to scale it. So scaled SI is going to be my historic value divided by this value, and you want to press F4 to put dollar signs, times the unscaled standard deviation. So 400 over 323 times this number, that'll give me the scaled standard deviation. And you can drag it down. And if you take this average, it should come out to 400 because you kind of rescaled it to 400. So now this is matching what I historically observe. Okay. Now I can get my order quantity. I have some quantity K. So let's say I put just 1 for K. Okay. So let's make it bold. Let's give it like a color. So this is my magic number K. I'm going to take the mean of each, the average value, plus K times the scaled standard deviation. And these are going to be my order quantities. Okay. I did not put dollar signs around K. So the K should have dollar signs around it. So when you drag the formula down, it still uses the same value of K. So notice any of these cells you pick up is picking up the right K. This cell, see, all of them picking up the right K. I'm going to round everything to whole numbers because there's no point ordering like half a jacket, right? And so these are my order quantities. Now, currently, these are not my final order quantities. I don't know the right value for K. I just picked K as 1, and these are just my initial guesses. So I can sum them and see, do they sum to 10,000 or not? Oh, they're way more than 10,000, so k has to be less. So let me do 0.5. Still way more. So let me do 0. Still way more. It's to be negative. Let's do negative 0.5. Still way more. So instead of randomly trying, because k can be positive or negative, right? So you have to try negative values. But instead of randomly trying, the values, I can just use the goal seek function in Excel. I go to data, what if analysis, goal seek. I want to set this cell, which is the sum of these, to be 10,000. So, because we have to order at least 10,000 because we can only keep 5,000 for reactive capacity, or the total 15,000. So set this cell to 10,000 by changing this cell k. So Excel will automatically try many different values for k until the value of k is such that it produces 10,000 down here. Here we go, 10,000 minus 1.25. Okay, so this is the right value of k. So let me fix it right here. I was doing multiple things and maybe I picked the wrong value from my Excel sheet, but it's minus 1.25. Okay, that k gives you 10,000. Okay, so this is the Fisher-Raman method to, we start off with very little information. Category level forecast, 15,000 units. Your capacity mix, what percentage efficient, 1% reactive. The efficient capacity mix, 67% times your forecast, tells you how much quantity you have to pre-order or order early. Now, how do you split the 15? How do you choose which SKU, how much to order? You put your forecasting team on the job. Each person gives you a forecast scaled so that the total is always 15,000, which is the category level forecast. Then you do this average, you do standard deviation, you scale the standard deviation, you pick a k, and it gives you the order quantity. So this whole process, Fisher and Raman showed that under certain relatively strict assumptions, this will give you the optimal use of the reactive versus efficient capacity. And right here is the reference to the paper published in Operations Research Journal. You can go to the library website, download this whole paper if you want to look at it. If you don't know how to download a research paper, there's an Ask a Librarian button on the library page, or you can email the librarian and they will send you this paper or help you get it. In any case, this is one way. Now, this has the assumption I want you to be a little bit careful about. The main assumption, which may be violated in reality. All of this analysis assumes that these items that are in the category, they have approximately the same profitability. Okay, so it's not that some of these parkas are very profitable and you make a ton of money on them, and the other ones you're just making peanuts on them. If that is the case, then you want to prioritize the highly profitable parkas, and we are not doing any prioritization like that, and then this may not be the optimal order quantities. Okay, and how to incorporate that becomes complicated, although it's not too hard, but it's too complicated for this stage. And so if you can get the main ideas and understand what we just did here, that's sufficient for now. As long as your category, your items can have different profitability levels. They should not be just extremely different. So you don't have something, like 3 times more profitable than something else in the same category. As long as that's not happening, you'll be reasonably close to a very good answer with this method. Okay. So I gave you all the formulas and I showed you how to do it in Excel. Find the average across the rows, the standard deviation across the rows, scale the standard deviation to match the historic forecast error, find the order quantity by picking a k of 1 or 0.5 or 0 or whatever, then using goal seek to pick the exact value of the k, which gives you the quantity you want, the total order quantity you want. Okay, and remember this one came from 67% of category level forecast, which was 15,000. That's how we knew that this has to be 10,000. Okay. Okay. Let's go back. Okay. So Here's the last point on the slide is the assumption I talked about. Using the same k-value for all of these items assumes that some items have all of these have similar profitability. If not, you might considering a larger value of k for the profitable items. So you may have two k values, and you might say that the k for profitable items has to be larger by a certain amount. So if it's minus 1.25 for profitable items, you may put the k to be -1, -0.5, something like that. And there are other ways. Even that, having a separate k is not optimal. In that case, what you want to do is you want to calculate the expected profit for every additional unit that you order, and use like a greedy algorithm to do it. But if you don't understand that, just ignore it. This out of syllabus for this course. Ignore how to incorporate different profitability levels into this. But don't worry, I'm going to show you, even without this calculation, just having the main setup of accurate response, like this process in place, even if you use very basic forecasting method and you don't use complex calculations, just having this process and having the opportunity of a second order with updated forecast, this gets you most of the benefit. Then this Fisher-Riemann type of calculation or some more complicated analysis like this one gets you even more closer to the optimal. And then, if you are then going into different profitability levels and using greedy algorithms, you're just trying to get the last few dollars out of the pie, but you're pretty much almost there with the simple calculations anyway. Okay. What if there are minimum order quantities? Because here, imagine, look at this parka Spain. We're only ordering 236. What if the supplier says, I'm not going to produce less than 500 of any parka? My MOQ, minimum order quantity for the supply, is 500. You can't order 236. Now, what do? Well, we have two options. Either we order 500 of the Spain parka, or we just don't produce Spain, because there's no way to produce 236 because the supply is not agreeing to it, right? And so sometimes if the order quantity is too low, look at the forecasted demand, 640. So you might have to just go for 500 in one shot, right? You can't produce 236. So you may have to up some of these quantities based on MOQs and reduce some of these quantities because they're well above MOQ to get to 10,000. So we have not factored that in. Okay. So what I want you to think about when you do have MOQs, okay, you want to look, you can assume that these SKUs have a normal demand distribution around this mean. Each SKU has a mean and a standard deviation. And so you can assume that there's a normal distribution of possibilities. It can be above the mean, below the mean, the demand possibilities. So if you assume that, you can calculate probabilities. Let's say the minimum order quantity is 600. Okay. So you have to order 600. Now, what if we order 600, at least 600 of each SKU, for what is the risk that we're going to end up with extra pieces of Spain and Gale if we order 600 units each? So look at Spain. The forecasted demand is 640. Standard deviation is 361. And Gale has 950 and 459. So we can use the normal distribution to calculate the probability that the demand ends up being less than or equal to 600. We expect the demand to be 640 for Spain, but there's a forecast error, there's a standard deviation. It might be less. We expect the demand to be 950 for Gale, but it could be less. So if the demand ends up being less than 1600, then we'll be left with extra pieces. So what's the risk of ordering the MOQ? If I order 600 for Spain, the probability that the true demand will be less than 600 is given by this calculation. In Excel, you type equals norm.dist. You put in the MOQ value first, MOQ 600, comma, you put in the forecast 640, comma, you put in the standard deviation for that SKU, the scaled standard deviation 361, comma, true, and that gives you a probability of 0.46. This means there's a 46% chance that if you order the MOQ of 600, you will be left over with extra pieces for Spain. For Gale, the chance is much less. Use the same calculation, and the risk for Gale is 0.22. Okay, so just interpreting this probability calculation, there is a 46% chance of excess unsold inventory for Spain and a 22% chance for Gale if the minimum order quantity is ordered for both of them. So if you order 600 for Gale in an efficient capacity and 600 for Spain in an initial capacity, Gale, we're probably going to be fine. There's only like a 22% chance that we're going to have extra units. So most likely we're going to sell all of the 600. But for Spain, it's like almost a coin flip, half-half. There's almost a 50% chance, or 46% to be exact, that your demand may be less than 600 and you may be sitting on unsold Spain parkas. By looking at this risk and comparing it given the MOQ quantity, you can figure out whether you want to produce the initial quantity, the initial order, because you can't produce less than 600. You have to go for 0 or 600. If the risk is worth taking, then you'll go for the MOQ quantity like it is for Gale. Okay, we'll take a 22% chance that we have some extra piece of Gale left over. Also because the MOQ is so far from the mean of 950 that even if we do have excess left for Gale, it's not going to be too much. For Spain, there is a good chance that demand may end up being 400 or 500 or 300, left with hundreds of Spain parkas, extra parkas. So for Spain, you might say, well, do I want to produce this parka? Maybe I'll just wait for the selling season. I'll not produce it now. I'll have 0 quantities. So I'll not have my own sales data, but I'll look at competitors. Are they selling a parka in the same colors as Spain and is it selling well? Then I'll put in an order for me as well. So you could do that. A lot of times companies will produce some minimum quantity of each parka to have their assortment. They want to show the customer that they're offering their choice. Okay. So we might order high risk items like Spain anyway if they're important to have an assortment for the customer. If we don't order an item early, in our first order of the season, before the season, then we'll not be able to observe initial demand. So we'll never know what the true demand for Spain is because we never ordered any Spain parka, right? And so if you don't order an item early, you're effectively canceling the item. You may still order it late based on some other signal, okay, like competitor is offering a similar parka, but you won't get your actual sales data from selling your own units. So it's up to you as a manager how you manage the risk. At what level of risk you're okay going for the MOQ. At what level of risk you say, okay, this parka, the forecast is so low, let me just scrap this and focus on other SKUs or something like that. Okay. So minimum order quantities complicate the problem even further. But again, just using rules of the thumb, okay, or just doing simple probability calculations like this and making certain decisions based on them, you can do a pretty good job. Fisher and Rahman, I don't know, in a different paper or this paper, they talk about how to handle MOQs, and it becomes like a very complex process. But, most of the time it's going to be clear to you, okay? If your forecast is in the ballpark of the MOQ, you want to order the MOQ, take the risk. Usually, if your forecast is very, very far away from the MOQ on the lower side, it's much, much lower than MOQ, then you might think about, okay, if I order the MOQ, I'm probably going to be left with a lot of excess parkas. Is it worth it to take the chance or not? And you make a yes-no decision based on that. And this kind of heuristic rule of the thumb approach will get you a lot of the benefit that the complex approaches will give you. So this is a very heartening slide. This shows you that even without calculations, just the accurate response setup of doing an initial order with efficient capacity, waiting for the start of the season, getting initial sales data, revising our forecast, placing a second order, just this setup gives you most of the benefit. So if we don't have the setup, look at the first column. Okay, this is data from Sport Open. If there's no accurate response, we were going to produce 172,896. We would have overproduced 83,000 units. Okay. And underproduce 14,000 units. How can you overproduce and underproduce at the same time? It's for different SKUs. Some SKUs we overproduced and we had too much of them. And we know we overproduced because the selling season ended and we are left with 83,000 pieces of these SKUs. And some SKUs we had a shortage. Customers still wanted that parka or that jacket or that whatever other products we sell, but we had nothing in stock. And so we turned away 14,830 customer orders, potential orders. Okay. Overproduction cost, because once you overproduce, you have to sell them at deep discount. So there's a cost to that because you lose your revenue, part of the revenue. The overproduction cost as a percentage of sales was 6.8%. Underproduction cost, which is the cost of lost sales, because you could have sold 14,800 more parkas, but you didn't sell them, so that's a lost benefit. That was 3.58% of sales. The total mismatch was 10%, 6.8 plus 3.58. This total mismatch, this is the cost of supply not matching demand. So you're losing 10% of sales. So for every $100 you sell, $10 you have an additional expense because your supply is not matching the demand. You either have too much or too low. So the cost of having too much is 6.8%. The cost of having too little is 3.58%. And you can see that they're leaning towards having too much. Like the Sport Obermeyer people, they generally order too much instead of too little, right? Because this cost is much more than this cost. Okay. So anyway, these are, and 10% is a huge cost. Imagine if you could match your supply accurately with demand, you could save 10%. Every $100 you sell, you make $10 more of profit. That is pretty huge, right? So the supply demand mismatch cost total is 10%. When you implement accurate response without any complicated mathematical calculations, you just have an initial forecast, you use the efficient capacity, you leave some of the SKUs which are unpredictable for reactive capacity, you observe initial demand, you revise your forecast, you use the reactive capacity. Just putting the system in place without any complex calculations gets you down from 10% of mismatch cost to 3.3% of mismatch cost. Overproduction has been cut by a huge chunk. Instead of overproducing 83,000, you're overproducing 25,000. Underproduction has been cut as well. You're producing too little of these. How has this been cut? Because if you made too little early on, you do the reactive capacity, the second order, you make up the shortfall. So you're not underproducing. You're not losing a lot of sales. Overproduction cost, the cost of producing too much, 1.74%. Look how much it decreased. Underproduction cost, 1.56%, total of 3.3%. Okay, so from 10.3, you're down to 3.3%. You get a huge benefit by implementing accurate response using very simple processes. Now we start using Fisher and Raman calculations, which are shown on these slides. This slide and this slide. How to use this calculation to determine initial order quantity. If you use these calculations, they give you a further boost. So instead of 3.3% error, your error is now only the cost of mismatch of supply and demand, instead of being 3.3% of sales, is now only 1.5%. But notice where the bulk of the benefit came. The bulk of the benefit came by implementing accurate response. The math part gives you a benefit, but it's not as big as fixing the process and having an accurate response in place. You can see that the overproduction didn't go down much, but the underproduction went down by a lot, right? Because you're using all of your reactive capacity, and once you get your accurate forecast, you're getting the additional quantity out from there. And so this really does a good job here. Okay. So Fisher and Raman calculations ensure low-risk units are produced early, high-risk units are left for reactive capacity. Because you use the disagreement of your different forecasting people to estimate a standard deviation. Then you scale that standard deviation based on historical data. That gives you a good estimate of risk. The key benefit of all of this is this scale standard deviation column, because it's giving you a measure of risk. And then your ordering quantity is a function of this risk. So you are really matching the risk. If you go back to this picture where you want to match the unpredictable items and the predictable items go to efficient capacity, unpredictable go to reactive capacity. This matching happens very precisely with the Fisher and Raman method because you're estimating the risk right here in this column. Okay, so if you do the calculations, you do get some benefit, but a lot of the benefit you get just by having some process in place. Okay, so that's how we do accurate response, right? I went into a lot of detail and I give you a lot of simplified yet very effective heuristics to figure out the order quantity, a heuristic method, which gets you very close to optimal. And I showed you the performance benefits. This is from the Fisher-Raman paper. This is what they tested it on Sports Obermeyer, their method and accurate response strategy, and this is what they found. So this is real data, albeit from 1990s, a little bit old data, but it is actual real data from a company on how accurate response helped the company. Okay, so let's talk about active response strategies overall. What are the strategies you can look at? A little bit of reactive capacity goes a long way. So only having 30% of your total capacity as reactive capacity, Sport Obermeyer reduced over and underproduction cost by 50%. So a little bit of reactive capacity gives you a lot of benefit. You can use simulations to determine the optimal level of reactive capacity to have given your demand uncertainties, because reactive capacity is expensive. You don't want to have too much of it either, more than you need, because then you're increasing your unit cost, decreasing your profitability. So you don't want to have too much of expensive capacity either. You can book capacity without specifying exact SKUs to be made till a later day. So some suppliers, they want to buy equipment, they want to hire workers, they want to buy raw materials, they want to confirm commitment on quantity. So you can tell the supplier, okay, I can't tell you exactly which SKUs what quantities to produce in the second order, but I'm going to tell you that the total quantity will be 15,000 units. And these are the initial orders up to 10,000. I'll tell you 5,000 later on, but the total quantity will be 15,000. So make sure you have enough workers, enough capacity for 15,000 production, right? So that's one way to get reactive capacity from suppliers. Book the total capacity that you know from category level forecast, and then figure out the SKU level quantities in 2 stages, initial order and then the second order. Increase component commonality. This way, let's say you are a car manufacturer, if you use the same transmission in 5 or 10 of your models, it's going to help you to be able to decide exactly how much of these models you produce on short notice, because you already have the transmission in store because you use it across so many different SKUs. If a particular model used a special transmission that only this model required, and if you decide I need more units of this particular car model, now you don't have the transmissions in stock because they were only needed for this SKU, and now you have to wait for the transmissions to be built, and then you can build this car, right? So component commonality really helps you out. The common components, you can have them in stock because one or more of those SKUs will sell well. So you can order, a lot of the common components. And then once you want to increase or decrease quantities of these SKUs, if they are based off common components, or they're mostly based off common components, you won't have to wait to get components produced and brought before you can start production or change production. Pre-purchase raw materials. Now, raw materials are very risk-free. If you have extra cotton, you can just build something else with that cotton, some other cloth next year or next season, right? If you have extra zippers, you're going to use the zippers in some sort of parka or jacket later on, or some other hoodie or something else, right? So raw materials, usually in a lot of industries, if they have a long shelf life, they're not very risky to buy in bulk because you'll end up using them, if not today, tomorrow. And what does that help you with? It helps you cut on your lead time. If you decide close to the selling season or during the selling season, you need more of a particular product and you don't have the raw materials, you have to first wait to get the raw materials, right? If you already have the raw materials, you can produce much faster. Lead time will be low. A lot of companies will purchase the raw materials and have them shipped to their suppliers. So the supplier will say, I'm not going to buy raw materials so early. I don't have enough working capital. The company will say, don't worry, we'll pay for it. And you just subtract what we pay for raw materials from your invoice when you charge us for the production. And so you have the raw materials on hand. So when we tell you to produce this much, you don't have to wait 1 month waiting for raw materials. You just start right away. So, component commonality, raw materials, book capacity without specifying products, all of these 3 points on this slide, their entire aim is to reduce lead time, to convert regular capacity to reactive capacity. It's a continuum, right? It's not that below a lead time of 60 days, now you have reactive capacity, at 61 days you have efficient capacity. No, it's a continuum. So you want to push your capacity to be more reactive by shortening the lead time. These are all ways to shorten the production lead time. Yeah. Postponement, so you produce a product almost all the way, but you leave the last few steps which determine the SKU. And because when you do decide to produce an SKU, you already have a semi-ready product. You can quickly do the last few steps, and your lead time to finish the product is much less. Let me give you an example. You sell shirts with different designs, logos on them, colors on them. But you can produce any of this shirt with a logo or a color from a plain white shirt. So you produce a lot of plain white shirts. When you figure out, okay, my aqua shirts are selling well and my orange color shirts are selling well, you just dye the white shirts into aqua and orange. My Jurassic Park logo shirts are selling well, you just stamp them with the Jurassic Park logo. It takes much less time to dye a white shirt, the right color, and stamp it with a logo than it does to start from scratch and first stitch the shirt and dye it and do XYZ. So that's called postponement. You do what you can before the selling season, and then you do the last couple of steps, the color or the logo or something like that, which differentiate the product into different SKUs. You do the last few steps, and then that's your short lead time of reactive capacity. You have semi-finished goods ready. You do the last few steps in the selling season to give you short lead time reactive capacity. The next one is obvious. We already talked about this. You want to use reactive capacity for products with unpredictable demand, or products that were relatively predictable, but you ended up forecasting them a little bit less and you want a little bit more quantity. You can do that too. Reduce forecast errors, because the amount of reactive capacity you need is a function of your forecast errors, unpredictability of SKUs. If you can improve your prediction, you need less reactive capacity. Let's say you needed 30% reactive capacity, but you found some way to improve your forecasting predictions and reduce forecast error. Maybe now you can live with 15% reactive capacity, and most of your reactive capacity is efficient capacity. So how do you reduce forecast error? Well, we'll talk about that in the next slide a little bit, some ideas, but sometimes it's not possible. A lot of times it's not possible, but sometimes it is. So you want to try to do that. You can also reduce minimum order quantities. The higher the MOQs, the less accurately your ordering is going to be, because you want something only 200 units, you end up ordering 600 because of MOQ, or you actually wanted 750, but it's MOQ is 600. So you say, okay, let me just do, then you could do 750. Above MOQ, you can order 750, but below MOQ, you have to increase those quantities to the MOQ level. So that's forcing you to order things you didn't really want to order. So MOQs cause inefficiency in the system. So if you can reduce MOQs, you can be more efficient. Okay. So let's talk about reducing forecast errors a little bit. Sometimes you can use demand data on some SKUs that are selling right now, today, to get an idea of SKUs that will sell in future. Let's say you are selling fall clothing, sweaters, hoodies, and you realize, okay, the pink color is selling very well in the fall clothing. It's highly likely that the pink color is also going to sell well in winter. So maybe you can use data on what colors are selling well and use that to improve your forecasting accuracy for the next selling season. Maybe because color trends last longer than 2-3 months, and data from today, the color data from today, which colors are going to be popular, can help give you better forecasting for the next 2 or 3 months. Let me give you a real life example. National Bicycle Company, I think it was in Japan. They would make custom bikes for people, and they would also have pre-built bikes that they would sell through retail stores. Now they realized that the design, the style, the color that the custom bike customers were choosing was correlated with what bike was selling well from the retail stores. So because custom bikes are produced after getting the customer orders, they're doing it all year round. Whenever they get an order for customer bike, they build it, ship it out. If you just looked at the custom bikes you produced in the last couple of months, that data was really valuable in predicting what bikes are going to sell in the next 2-3 months in retail shops. So they use the custom bikes attributes of that, which color, what features are popular. They use that in their forecasting system to improve forecast accuracy of pre-built bikes in the retail shops. Now you can get early signals like construction permits if your products relate to construction or homes or buildings, right? So if you can find an early signal, a leading signal, or you can find a product which is correlated with a product you're going to sell next season, and you can use this product's data to forecast the other product more accurately, these sorts of strategies can help you reduce forecast error. Another thing you can try is machine learning algorithms. They can combine a lot of data, including data we just talked about right now, and they can find correlation between different products, and they can sometimes often outperform, the simpler time series methods. If you look at the recent forecasting competitions, almost always machine learning algorithms are beating, ARIMA models or regression-based forecasting, those sorts of models. So you can look at newer techniques in forecasting and see how well they apply. And sometimes these algorithms can give you, because the time series methods like ARIMA, exponential smoothing, time series decomposition, all of those methods work well when you have a lot of historical data. So you need to apply them at the category level. The machine learning algorithms based on features of the products can sometimes do a decent job at the SKU level as well. So in this column of the 5 forecasters, maybe you had a 6th forecast, which is the machine learning algorithm. And maybe the 7th forecaster is a different machine learning algorithm. So you can combine human judgment forecast with machine learning forecast too. Right? Okay, so this out of these strategies we talked about reduce forecast errors. We're going to talk about postponement. The reason we're talking about some of these strategies in more detail is they're really important, right? They're really useful. So postponement is the ability to delay product differentiation, such as colors or customization, until we are very close to the product being sold, or the customer has already placed the order and now we can quickly customize it and ship it out. Okay. Why? Because it's easier to forecast the demand for all t-shirts, but much harder to forecast the demand of the orange t-shirt with the Jurassic Park logo. Right? So if we can delay the differentiation, we just forecast demand for all t-shirts and we just produced a bunch of simple t-shirts, then we just dye them and put a stamp and ship them out once the customer goes to our website and orders the Jurassic Park t-shirt. Common components help you with postponement. Postponement reduces the cost of reactive capacity because only those steps need to be part of reactive capacity where the product differentiation occurs. Crocs is a company that used postponements very effectively to reduce lead times of production. Okay. They used to have colored pellets with many different colors. Okay. So they would buy these plastic pellets. They would buy red plastic pellets, blue plastic pellets, green plastic pellets, and they would make the shoes with those plastic pellets. So if you wanted a green Crocs shoe and you were and you didn't have the green pellet, you could not make the green shoe. Okay. So what they did, instead of buying these colored pellets from suppliers where there was a lead time, so if you wanted more green pellets, might take you a month to get more green pellets, they started making the colored pellets in-home. They started getting dyeing or putting the color in the pellets in their factory. So if you needed green pellets, so just run a batch of green pellets and in the next 12 hours, you have green pellets to make green Crocs. So that reduced their production lead time a lot because then you don't have to wait for the supplier to give them specific color pellets. They just get some neutral color pellets and they do the coloring compounding in their factory. What does this do when you reduce your lead time like that? Now you can place multiple orders in the selling season, or you can wait for more of the demand to be observed and then place orders. So your reactive capacity has a shorter lead time, or your normal capacity has a shorter lead time. It's more like reactive capacity and so on. So whenever you can reduce lead time, it is moving towards reactive capacity or making your reactive capacity even better, and that will help you because if you can observe more of initial demand to place the second order, you're going to be very accurate. You're going to hit the nail on the head and you're going to match the demand with supply. How do you evaluate performance of accurate response? We already talked about it in this slide. You look at overproduction cost and underproduction cost. Overproduction is cost of excess. You have too much. Underproduction is cost of shortage, which is lost sales cost. The total of these two costs, this cost in the last row right here, the mismatch cost, that's the cost that's your performance metric for accurate response. The lower this total cost in the last row, the better your accurate response is working. So you want to track this cost. You want to track this performance of accurate response, and you want to get better over time. Okay. The problem is, how do you know the cost of underproduction? If you produced less of a particular SKU and you're having lost sales are not visible in your IT system. They're not visible anywhere. You don't know if there was a lost sale or not. All you see in the IT system is, okay, some SKUs have zero inventory, but there's no record of customers who are coming and asking for them. So how do you measure lost sales? So a lot of companies will do a statistical approach. So whichever time period where you have zero inventory of an SKU and you are supposed to be selling that SKU, they will use the recent sales data to project that forward and say, okay, the past 2 weeks we sold 100 pieces per week. This week we have zero inventory, but we're going to project, okay, we would have sold 100 if we did have inventory. So use a statistical approach to estimate, lost sales are like missing values. You don't know what the sales would have been if you had inventory. Because you didn't have inventory, you didn't observe the sales. So you can fill those missing values by just projecting the past into those missing values and say, the last week we had this much sales, so this week we expect to have had this much sales. If you do take back orders, customer back orders can show you lost sales, because for a back order, you may have to give the customer a discount or expedite the order. So there's a cost to back orders. And then the cost of shortage is the cost of back orders. But the back orders capture your lost sales, or the sales which is not really lost. You are going to fulfill this demand, but you're going to fulfill it in a different manner as a back order. You can train if you have sales staff in the stores. Let's say you're a high-end shoe store and you have a lot of sales staff. They can record if they missed a sale because a particular color or size or SKU was out of stock. So anytime a customer says, oh, I really like this shoe, can you give me this shoe in size 10? And you don't have size 10 in stock, you make a note in some IT system or on some piece of paper that this SKU, this size was not in stock, so I lost a sale. And then that data can be collected, and that can be a way to estimate lost sales costs. If you can estimate lost sales costs by any of these approaches, then you can estimate the underproduction cost as a percentage of sales, and then you can estimate the total mismatch cost, which is telling you about how well your accurate response is working. So that is the end of accurate response lecture. It was a lot of information to absorb, but the key idea is really simple. This slide right here, this slide, and this slide, these three slides give you the main idea. If you want to review what is accurate response, just review these three slides. If you want to review the Fisher and Raman method, review the part where I went over these two slides in Excel. So you can calculate the average easily in Excel. You can calculate the standard deviation easily in Excel and just rescale the standard deviation. So your forecast error is the same as you expect from based on historical data. And then you use goal seek in Excel to figure out K to determine order quantity. So not too difficult to do either. You can re-watch that part of the lecture, right? So that is, in short, you have a new superpower now. Accurate response is a big part of certain supply chains, fashion clothing supply chains. The Crocs supply chain uses accurate response for shoes. So in many cases where your product has a short selling season, it doesn't sell evenly. Even electronics sometimes, Black Friday. You get back to school sale, August, September. Then you get Black Friday, and then you get Christmas sales. So you have like 4 months time period of the year where you have a lot of discounts, a lot of promotions, and sales going through the roof for some SKUs. So you can, for electronics even, you can think of that as a high selling season, and you can plan for the selling season using accurate response strategies. The response to your laptops that you sell in back to school sales will tell you something about how people will respond to the same laptops in Black Friday sale. right? And so you can use the back to school sales data to use reactive capacity to produce more of those laptops in time for Black Friday, right? And so you can use this in a lot of industries.